welcome back to my channel, and today this is part 5 of recurrence relations using linear algebra. Okay, so if you haven't watched the first, second, third and fourth part of the videos, please go and check those out first. You can find those in the I tab above, and today we will continue in this part 5 from where we had left off in part 4. In part 4, we discussed till the intuition behind what is the meaning of S, what is the meaning of S inverse, where S is the eigenvector matrix. S inverse is the inverse of that eigenvector matrix, and lambda is nothing but the matrix having diagonals as the eigenvalues, right? This matrix A, any matrix A can be represented as S lambda S inverse. We discussed the intuition behind it. Now we will move on in the part 5 and represent this recurrence relation in terms of eigenvalue, this decomposition S lambda S inverse. How do we write it? Okay. So let us see. Okay. So this was our matrix, right? So we will just copy this part out. Okay. Let us copy this part out to a new page. Okay. So this was our recurrence relation, and this was our U naught. Sorry, not U naught. This was our UN, because this matrix is giving us the nth term, right? Nth term using the n minus 1 and n minus 2th term. So what we will do, this matrix we will call UN. Okay, but I know the initial conditions. Okay, we will go to the first page. Yeah. So this was our initial condition. We know that A0 is the 0th term for this recurrence relation is 1 and first term is 2. Okay. So we have to write in terms when our inputs are known, that is A1 and A0. Okay. So how do we write it? Okay, I know that U1, U1 means U0 is this. Okay, U0 is this. Using U0, how can we write U1? Okay, so U1 will be nothing but A1, A0. That is the first term of the sequence. Using the 0th term is equals to 3, 1, minus 2, 0. That is the A matrix. And the input will be U0. A1, A0. We know the values of A1, A0. We will substitute it over here. Yeah. Okay, wait. We already know A1, A0, right? So we will assume this is our U1. Okay. This will assume as our U1, and using U1 we will write our U2. This is our U2. Or we can write like this only, no problem. We can write, if this is our U0, then our U1 will represent the second term, the bigger term than A1. Okay. So we'll just erase. Okay. We will write A2, A1, using A1 and A0. Then our input would be A1, A0, our U0. Okay. Now, can I write U2? U2 means, okay, we'll add a new page. Can I write our U2? That is nothing but A, this was 2, I want A3. A3, A2 will be equal to our A 3, 1, minus 2, 0. 3, 1, minus 2, 0. Times, I know this side what will be it be. The input would should be A2, A1, the previous two terms, A2, A1, right? You can get A3 using the previous two terms, A2, A1, that is the U1. And I know how I can write A1, U1. U1 is this, right? So if we substitute this over here, this is what your U1. If we write U1 in terms of A U0, then we will just erase this and write again A U0, 3, 1, minus 2, 0 times U0. U0 was A1, A0, and we already know the value of A1, A0, the base case condition, right? So that means U2 can be written as, if I substitute this as A into A, okay, one matrix we will write as A, right? This matrix is your A. Then this would be A square times U0, and this is your U0, right? Similarly, U3, if you write, U3 would be your A4 using A3, right? Is equal to A 3, 1, minus 2, 0, and the input would be your U2. And I know what is the value of U2, it's A square U0. That means 3, 1, minus 2, 0 again. 3, minus 2, 1, 0 times U0, A1, A0, right? So that becomes U3 is equal to A cube times U0. So if you see the pattern, okay, if you see the pattern, and U1 is nothing but A U0, A power 1, right? So if you see the pattern, what is with U, what subscript is there? Same power of A is there, right? See, A2, U2 was having A square U0, right? U3 has having A cube U0. So that means our nth term Un would be equal to, if we generalize, A power n times U0, right? And we wanted the closed form. Now we have to take the nth power of a matrix. How do we do that? We can represent this matrix A in terms of S lambda S inverse, right? And we discussed the intuition, what S inverse means, what lambda means, what S means. And we found out the value of S inverse and lambda also in the previous parts of the video. Okay, if I take, means we have to take a power of this, nth power of this, and we know in eigen, S inverse is converting the original inputs in eigen coordinates, and in eigen coordinates, any power of transformation matrix is nothing but the power of the eigenvalues, or just a stretch. So that means, okay, I will add a new page. Our A matrix is becoming S lambda S inverse. That is equal to, we will substitute the values. Okay, we found out in the last video. Our S inverse is 1, minus 1, minus 1, 2. Okay, 1, minus 1, minus 1, 2. Our lambda eigenvalues were 2 and 1. Right? Let's see it once. Yes, 2, 0, 0, 1. 2, 0, 0, 1. And what was our S? 2, 1, 1, 1. Okay. So now if we take the power of a, nth power of a, then we have to take the nth power of this whole thing, and that is nothing but, in eigen coordinate system, it is nothing but uh, 2, 1, 1, 1. Okay, this is equivalent to this 2 power n 0, 0, 1 power n. Okay, 1 minus 1 minus 1, 2. This is the speciality of eigen coordinate system. Okay, so that means if we calculate this, this will come in the form, see, a constant, this is a scalar, this is representing a scalar, and it will be multiplied with the columns of this lambda vector, right, lambda matrix, and again this is will be become, after multiplication we will get, okay, let us see what we will get. Okay, so 1 times this and minus 1 times this, if you add, you will get 2 power n, okay, and minus 1 power n, okay, and yeah, minus 1 times this, okay, minus 2 ki power n, and 2 times this, right, 2 ki power 2 into 1 power n. Okay, so if we have to add these two, so what will happen? So this will be nothing but 0 and 2. Wait a second. Okay, let us continue again. So 1 times this column, right, we will get 2 power n minus 1 times this column, right? So you get minus 1 into 1 ki power n. That will be nothing but, this will definitely having a minus sign. And this is the first vector, plus minus 1 in times first column, right? So that would be minus 1 into 2 power n. So that will be minus outside 2 raised to the power n, and then 2 times this column. So that will be 2 into 1 power n. So if we add, then what we will get? We'll get this, and this will become 0, and this will become 2 minus 1, right? This is 1. 2 minus 1 is 1. 1 into 1 power n. Okay, so I will write it above over here after raising this. This matrix will become, this multiplication now becomes 0 into 1 ki power n, right? This matrix multiplication. Now this has to be multiplied with 2, 1, 1, 1, right? So what will happen? 0 times first column, 1 ki power n times second column. So this would be 1 power 1 into 1 power n, right? And 1 into 1 power n. That is equal to our un, right? Yes, this is our un. And what was un? So this is nothing but 1 power n. That is equal to, we will check what was our un. Yes, n plus 1. Whatever n is, that 1 bigger than that is the term. So this would be equal to a n plus 1 and a n, right? So our a n, nth term, 1 into 1 power n. Okay guys, here we calculated S lambda S inverse, right? This was S lambda S inverse power n. But you have to multiply. This is just A power n, right? To get un to this, you have to multiply your initial u0, right? u0 was a0 multiplied by a, a1 and a0, right? a1 and a0. A1 and A0, and what was the value of A1 and A0? Our initial base case condition 1, 2, 2 and 1. So we have to multiply it with 2, right? So we have to multiply it with 2, 1, right? Then only you will get UN. So that is, and UN was our AN plus 1 and AN. This was our UN, right? N plus 1th term and nth term. So from here we get nth term as this 2 into 1 whole will be multiplied by 2, right? Okay guys, we have to note that in matrix multiplication, we cannot pre-multiply the matrix. The order of matrix multiplication is important, right? So we will redo from here. The order of matrix multiplication is important because it's a linear transformation, right? So we know in matrix multiplication, AB is not same as BA. A times B is not same as B times A, correct? Because here the basis is B and the basis is A over here. So the matrix commute is not commutative. So from here only what we have to do is, here we have to multiply with u naught as well. Then only it will work. Okay. So this would be nothing but 2, 1, 1, 1 times 2, 0, 0, 1 times this power n, right? This power n, 1 minus 1 minus 1, 2. And u naught is our, what is the value of u naught? 2 and 1, right? 2 and 1. Okay, let us multiply now. So 2 times the first column, okay, so this would be 2 minus 2. 1 times the second, that is minus 1, 2. And you have to add both. So that would be 1 and 0. Yes, now it is coming correct. 1 and then a 0. Okay. This will be multiplied with 2 की power n, 0, 0, 1 की power n. Okay. And 2, 1, 1, 1. Always remember, you cannot pre-multiplied S lambda S inverse power n and then multiply with u naught. It will not give you the same answer. Okay. I will make a separate video telling you why matrix multiplication is not commutative. Okay. So 1 times this column and 0 times this column will give you 2, 1, 1, 1 times. Don't make this mistake. This is a silly mistake. Okay. Basic conceptual mistake. 2 power n times 1 and this would be 0 only, right? So this will result in, now we will multiply this column. What we will get? We will get 2 into 2 to the power of n and 2 to the power of n, right? This will be your equal to un. And un is nothing but an plus 1 and an. So from here, what do we get our an as? Our an is 2 to the power of n. This is your recurrence relation. We will add another page. Our an is equal to 2 to the power of n. That is our closed form of the equation. We will check it is generating the sequence or not. If we put n as 0, a 0 is 2 to the power of 0, that is 1. That is correct. Our a1 is 2 to the power of 1, that is equal to 2. That is also correct. We saw, right, in the beginning, right? 1 and 2. Our so base cases are coming correct. Now our from the recurrence relation, if we see what is our a3, our a3 should be 3 times a2, a2 minus 2 times 2 minus right, this is 3, right? 3 minus 2, 1, a1. So that is 3 times a2, right? What is a2? What is our a2? Okay, okay, this we started from 0, right? Okay, now let us take this as a1 and this as a2. Okay, then a3 would be equal to, third term, next term would be equal to 3 times 2 minus 2 times 1, that is 6 minus 2, 4, right? So a3 should be 4. Let us check. A Okay, wait, we are stated taking from 0 only. Okay, okay, let us then find a2 first. Okay, what is a2? Okay, a2 will be equal to 3 times a1 minus 2 times a0. Okay, a2 will be equal to 3 times a1. So this will be our a0 and a1 only. Okay, this would be our a0 and a1 only. Okay, a1 is 2 minus 2 times a0 would be 2. 2 into 1, right? So 6 minus 2, 4. A2 is 4. Let us see. A2 is coming out to be 4 or not. A2, 2 power 2, 4. So this is also correct. So this is our general form of the recurrence relation. Now in your exam, if you don't need to find uh, you don't need to show you solving recurrence relation using eigen linear algebra, then I will tell you a fast trick to calculate the recurrence closed form of the recurrence relation without finding s and s inverse. Okay, and but this formula has come from this basic concept of a power n s lambda s inverse power n only, but we will just generalize this part over here. Okay, we will just generalize. Okay, and we will convert this matrix form into lines, row view means lines that which are intersecting. Okay, line view. And we can find the closed form of recurrence relation faster in that way. Okay, hope you like this video. Please share it with your friends, subscribe to my channel, and keep looking about how you can apply discrete mathematics in your everyday life. Bye bye and